Hey guys, welcome back. We're going to continue working with the Pythagorean Theorem today. We're just going to try to find those right triangles in different real-life situations so that we can find unknown lengths. So our learning target today is again to know and apply the Pythagorean Theorem, but this time to real-life situations, and also calculate distance specifically in the coordinate plane. So our success criteria on this, recognizing right triangles in real-life situations, we may have to look at 3D objects to try to see the right triangles that are there. Second, I can use the Pythagorean theorem to solve for unknown lengths. Again, distance formula in the coordinate plane, or also unknown lengths on different 3D objects, or also just in plain old right triangles where there are unknowns. And lastly, I can use the Pythagorean theorem to find distance when points are plotted. And that's what I'm talking about with the distance in the coordinate plane. So let's look at the first example. Some of what you're going to see is going to have to do with pyramids. The Great Pyramid is a square pyramid. Square pyramid meaning there is a square on the bottom. Okay, so this right here, even though it kind of looks like a diamond the way it is right now, since it's 3D, that's just the perspective. If you were to actually tilt the pyramid on its bottom, the bottom of the pyramid would look like a square. To the nearest hundredth, what is the slant height of the Great Pyramid? Slant height is this guy right here. It's always going to be signified as like a cursive L. Okay, so I'm going to make a little note of that. Slant height is equal to cursive L. And if you notice in the picture here, slant height does exactly that. It's the length that goes along the slant of the pyramid. Okay? The actual height of the pyramid goes from the tippy top to the center of the square base. Okay, so this is the actual height. Think of like when you stand up, you stand straight up. Okay, you make a perpendicular or a right angle to the ground. That's how you know you're standing straight up. You form a right angle with the ground. Okay, so this dimension right there, that would be the actual height of the pyramid. But then the slant height goes along the slanted part, okay, which they've signified as the cursive L. So in this example, we want to know how long the slant height actually is. They give us that this distance here is 230.35 meters. Now, if you were to draw a line, which they've already actually drawn a line, a dotted blue line, I'm just going to bold that. Okay, so this line right here, the height of the pyramid, the point to which the height of the pyramid intersects the square on the bottom is in the center. So what I can do here is there's kind of like another 3D distance here, okay, which it's like the height of the square on the bottom of the pyramid, which cuts this side in half. Okay, these two pieces would be equal, which is exactly what this dimension, okay, let me go back here, this dimension right here, okay, that's exactly what that dimension is, which is this number. If you were to take 230.35 and divide it by 2, you're going to get 115.175, which is this number right here. So what I'm trying to get at is sometimes you may have examples where they give you this entire length and they do not tell you what this length is, but you need it. You need from here to here. You do not need from here to here. So if they ever give you the entire distance, cut it in half and you'll get the distance that goes from the center of the pyramid to the edge of the pyramid. Because that's what you need to create this right triangle that's standing up inside the pyramid. Okay, it's like if there was a pole in the center of the pyramid kind of keeping the pyramid standing. Okay, it forms that right triangle with the side of the pyramid. So it's going to look like it's inside the pyramid, the right triangle. Okay, so now that we've kind of seen where this right triangle is that is forming from the slant height and the height, all we're really doing once again is plugging into the Pythagorean theorem. Now, since this is the right angle right here, that means that these two lengths are the legs. So it doesn't matter which one we call them. Let's just call the height A, and we'll call this half base distance B. And then the L really is the C value of this right triangle. So my Pythagorean theorem says a squared plus b squared equals c squared. Well, a in this situation is 146.71 squared plus 115.175 squared is equal to c squared. Okay, now what I would do is I would plug these numbers into your calculator and do not round until the very end if you have to. So I'm going to go to my calculator and I'm going to type 146.71 and then square that. So I want you guys to write down that entire number. Okay, I know it's a long number, but write it down because we should only round at the very end. Okay, then plus, again, go to your calculator. Okay, type in 115.175, square it. All right, now we want to take down that big long number. Yeah, whew. Okay, lots of big numbers there. And then equals c squared. Now I have to add those two numbers together. Now what I'm going to do is I'm going to keep that big, long, enormous number in my calculator, and I'm going to add this number to it. All right, so I'm going to keep that number plus, let's see, we had 21523.8241. Whew, got that big long number that I have to write down now. 34789.10475. I'm going to double check that real quick. 0.104725. Okay. Is equal to c squared. And now I'm just square rooting both sides. Now this is where you can round your final answer. So I'm going to set it up. I've got c is equal to. Now some calculators you can just keep that number in there and just hit the square root button. I believe in my calculator I have to hit the square root key first. So what I'm going to do is I'm going to hit square root. Yeah, see it's already wanting to times that number by square root. So I'm going to delete that. And then I'm just going to hit, see, clear. I have it in my history there. So I'm going to clear it out. I'm going to write square root, and then I've got it on the left side, 34789.10475. Okay. And there's my answer. The instructions didn't really have any rounding directions. In this case, you can go ahead and round to the 100th, or you can round to the 10th. I'm just going to round to the 100th. 186.52. 186.52. And it looks like they have this in meters. So I can say the slant height of this pyramid is 186.52 meters. Okay, so now what I would like you guys to do is give this a try in your first U-try. Again, I want you guys to see the triangle that is standing up inside of the pyramid. It says to the nearest 10th, so it does give you some rounding directions. What is the slant height of the square pyramid? Now the slant height goes from the top and connects down the slant to make that triangle. So right here, that's the slant height. Okay, now they don't give us this length right here, but again, we talked about how this length is half of this full length right here. Okay, because this point right there is in the middle of the square. So all you need to do is take this length, cut it in half, and that's what you're going to get for this length. Once you solve that, you should be able to plug into the Pythagorean theorem. Give it a try. Alright, so I've got one more you try for you guys, only I'm stepping it up a little notch here. I've taken away some of the different like inner drawings on the triangle. I want you guys to be able to find the right triangle that would signify having the height and the slant height, and then I would like you to find what that height of the pyramid is. Okay, so using the techniques that I showed you from the example and what you've just seen in the key of the first you try, I want you to try to find the height of this pyramid. Now remember, the height goes from the top of the pyramid to the center of the square. Go ahead and give this one a try on your own. It's a little bit more difficult, but try it on your own first, and if you can't get it, then go ahead and ask a question. Alright, so other than looking for unknown lengths that are inside of 3D figures, I think one of the most useful ways to use the Pythagorean theorem is to find the distance between 2 points. And I mean the direct distance. So think about a coordinate plane as being like cross streets. Okay, when you drive, you know, you're going down the road, you take a left, you take a right, okay, that's your path. Okay, but the most direct route to go from A to B is a straight line, which is usually diagonal and not just, not just following streets. Kind of like if you were going to your friend's house, but instead of following the sidewalks, you cut through people's backyards because it's a shorter distance. Well, we can't just count by following grid lines. We can't just count units when lines are diagonal like that. So I'm talking about, let's say you have these 2 points in the coordinate plane, that point right there and this point right there. Okay, if I want to know this distance, okay, the straight line distance, we would draw in the legs of a right triangle in order to be able to count the distances. So like in this one particular, we have 1, 2, 3, 4, 5 units is A, and 1, 2, 3, 4, 5, 6, 7 units is B. Okay, well, the right angle connects the legs of this triangle, so I would just apply a squared plus b squared equals c squared to find the distance. So anytime you're trying to find the distance between 2 points in the coordinate plane, draw a right triangle between those 2 points, and then use the Pythagorean theorem and solve for c. That's going to be the straight line distance between them. So let's try this in the second example. It says, what's the distance between A, which is -2, -3, and B, 4, 5? So let's use our grid paper here and draw a coordinate plane. Okay, my 2 points, I have one that's in the third quadrant, one that's in the first. So let's just center our axes as much as we can here. That didn't look very centered. There we go. That's good enough. Even if it does look like it's a little too far to the right, the points should still fit. I have -2, -3. Okay, so -2, -3 would be down there. And then I have, what was it, 4, 5. Okay, so +4, +5. That's up there like that. Okay, now again, the shortest distance between any 2 points is a straight line. But we cannot count the units since that line is going diagonally across the coordinate plane. So from each point, and I don't care if you draw the triangle above or below, just follow along the grid lines. And if you need to, you can extend it like that so that you know that you're not accidentally drawing a diagonal line. See how as I'm drawing my pen, it follows the diagonal or the grid line. Okay, so you don't have to overshoot it like that, overextend it. If you can, stop where you see the point right above it and then connect them together. When you are intersecting and you see a box there, that you know you're forming a right angle. A completely vertical line meeting a completely horizontal line is going to form a right angle. So that means I can now count the side lengths I've marked in red. I see 1 unit, 2, 3, 4, 5, 6 units here. 1, 2, 3, 4, 5, 6, 7, 8 units there. And again, these are the legs of my triangle. So let's call this one A and call this one B. And then again, we'd be solving for the hypotenuse, C, and the C is going to be our distance. So I'm going to again write my Pythagorean theorem. A squared plus B squared equals C squared. And for A, I would have 6 units, so I have 6 squared plus, oh, no, actually I labeled that as B, sorry. Okay, A, I have 8 units, so 8 squared plus B squared, which is 6 squared, equals C squared. Now, technically, it doesn't matter which one I plug in for A and B. I could have written 6 squared plus 8 squared equals C squared. It really does not matter the legs. Okay, the most important one is C. C is always across from the right angle and is the longest side of the right triangle. So let's now square these and solve for C. I've got 64 plus 36 is equal to C squared. 64 plus 36 is 100. And then if I square root both sides, the square root and square go away. We're left with C is equal to 10. So in this example, the distance between point A, which is at -2, -3, and point B, which is 4, 5, is actually 10 units in length. Let's have you give this a try in your second U-try. Give yourself some axes. Make sure wherever you put the axes, you're able to see your 2 points, A and B. Okay, don't let them fall off the graph. You can put the axes wherever you want. You can put them over here. You can put the axes over here. But I want you to choose where the axes should go in order to fit both of these points on the grid lines. Then just follow the steps we did from the example. Make your right triangle and use the Pythagorean theorem. Give it a shot. Alright, I've got one last example for you, just a straight up triangle. I want to know if this triangle is in fact right. The only twist on this, which is different from yesterday's example 4, was that some of the lengths of these triangles are written in radical form, meaning those numbers that you see have a root over them. And this is actually the most exact way to write a number if you do have to take a square root of something that is a non-perfect square. So I find these problems easy though because the Pythagorean theorem, again, I'll write it again because that's how we memorize things. A squared plus B squared is equal to C squared. It has squareds in it. Squared, squared, squared. Well, squaring something is the opposite of square rooting. So don't look at this as being scary. Just plug it in like normal. Now again, the largest number is going to be the hypotenuse. And if you're not sure how big the square root of 15 is or how big the square root of 21 is, then you can use our approximation skills that we had. Okay, so the number 15 is between what two perfect squares? Well, it's between 9 and 16. So the square root of 15 is going to be somewhere between 3 and 4. Okay, so it's going to be 3 point something. That's definitely less than 6. Same thing with the number 21. 21 is between 16 and 25. So the square root of 21 is going to be somewhere between 4 and 5. So it's going to be 4 point something. So 6 is the longest side here. 6 is our C. So that means it doesn't matter where we plug the root 15 or the root 21 for A or B, as long as we plug 6 in for C. So let's do that. Let's plug into the Pythagorean theorem and we'll see if this triangle is right. Because again, if the Pythagorean theorem holds true, then it has to be a right triangle. So I'm going to plug this in for A, square root of 15 in for A. I'm going to plug square root of 21 in for B. So I have the square root of 15 being squared, because it's A squared, plus the square root of 21 being squared, because that's B squared, and then equals C squared, which is 6. Now, if you want to put parentheses around the 6, you can, just so that they all look the same, but you really don't need it. Okay, I only put parentheses around these because I was mixing a radical symbol with a square symbol, and I just wanted to make sure you guys could tell I'm squaring a root, which in fact makes this problem easy because when you square a square root, they cancel. That's how we would solve problems earlier. So what you're left over is with 15. Okay, if you square root 15 and then you square it again, it goes back to being 15. Same thing with the square root of 21 squared. Okay, these are inverse operations. They undo one another. So you're just left with 21. And then 6 squared is 36. Now I'm just adding these two together to see if they're true. 15 plus 21 is in fact 36. So my equation is 36 equals 36. That is true. That is a true equation. 36 does equal 36. So what that means is this triangle is right. Okay, and our justification is this plugging into the Pythagorean theorem part. Okay, that tells me when I plug into the Pythagorean theorem that the equation is true, so it must be a right triangle. Let's have you guys give this a try in your third and final U try. All right, so I'd like you guys to give this one last problem a try on your own. Try drawing a picture of what you think this situation is representing. We've been studying the Pythagorean theorem and we've been studying right triangles. So picture this as creating a right triangle and label each side with the blocks that they tell you. Then use the Pythagorean theorem to find the distance they're asking for. Alrighty, so that basically wraps up our lesson for today. We got to know and apply the Pythagorean theorem to real-life situations, and we calculated distances. In order to do this, we recognized right triangles in real-life situations, like thinking about streets intersecting with each other, forming right angles, talking about pyramids, seeing right triangles being formed from the top of the pyramid to the center of the square base. We also used Pythagorean theorem to solve for unknown lengths. That was like in example 3. So I'm going to say our first success criteria we found in both examples 1 and 2. The second success criteria we can find in example 3. And then the distance formula was example 2. Okay, so we did all 3 of these success criteria. If you can say you can do all 3 of these, then you'll be fine on your homework and you'll be able to do the problems on the test. If you don't understand something in this lesson, please go back and rewatch any sections you may need to. Raise your hand and get any help so that we can maybe explain it to you differently if it's not really making any sense. And please do not move on to your Google form homework till you feel comfortable with being able to use the Pythagorean theorem in many different real-life ways. All right. Go ahead and start your Google form, and you may have a great day.